Okay, today we are starting the chi-squared distribution chapter, which is chapter 11. So first of all, just some properties about the chi-squared distribution. First of all, it's a family of curves, similar to what we had talked about with the t-distribution. It's not just a single curve like the normal curve is. It changes based on the degrees of freedom. So in the picture to the right here, we have three curves that are shown. The first curve would have a degree of freedom of 1. The red curve has a degree of freedom of 5. And then the green curve has a degree of freedom of 10. So as we can see, for small degrees of freedom, the chi-squared distribution is extremely right skewed. But as those degrees of freedom increase, the skew gets less. So the red curve is less right skewed, but the right skew is still evident. And then for the green curve, it is even less right skewed. It's looking more like a normal curve, but it never really reaches a normal shape. Okay, so it stays right skewed the entire time. What it does is it measures difference from what is expected for categorical data. So this is the first curve, guys, that we've looked at that hasn't been numerical. So this is used for categorical data. So categorical or qualitative data is like hair color. And so we'd be looking at the frequency of each hair color, or the number of M&Ms in a bag. So the different colors of M&Ms. This curve has both horizontal and vertical axes. So before, the normal curve was just set on the horizontal axis, and it ranged from z-scores of approximately -3 to +3. If we notice, the horizontal axis on the chi-squared distribution starts at 0, so there are no negative values, and it increases as we move to the right. The horizontal axis then will always be positive values. The vertical axis is still representing the probability. So we have an area under the curve of still 1. Okay, and then as I mentioned earlier, it still has degrees of freedom, but the degree of freedom is not the sample size -1 like it was for the t-distribution. It's the number of categories that we have -1. So some differences there with the chi-squared distribution chart. Okay, here is part of the formula sheet that we were given at the beginning of the course. So pull out that, guys, and locate your chi-squared distribution chart. This is the first time we've used it, so it might be back in those folders a long way. But in the first vertical column, we have degrees of freedom, similar to how we saw the t-chart set up. And then across the top, we have common alpha values. We will pretty much be using the right half of the chart because we're going to be dealing with alpha values between 0.005 and 0.1. Okay, so we would go down to a particular degree of freedom. Again, the number of categories that we have -1. And then we would move across to a particular alpha value that we want. And this is how we would find the critical value. We're going to do a couple of examples in this next slide. Okay, so I've zoomed in on part of the chi-squared distribution, so it's a little bit easier to see. And we're going to go ahead and find critical values for these 5. We're going to do the first 3 together and then pause the video. You guys try the last 2 and then unpause the video to get those answers to see if we're doing those correctly. Okay, so let's take a look at the first 3 together. So the first one says that we want degree of freedom 2. So we're going to go down to degree of freedom 2 line. And we go across to the alpha equals 0.05 column. So as we can see here at the top, alpha is 0.05 for a degree of freedom of 2. We're going to see where those meet. Okay, right here is where those 2 meet. So our critical value is going to be 5.991. 5.991. Okay, let's take a look at number 2. Number 2, we want degree of freedom 7 and an alpha of 0.01. So I'm going to go down to the degree of freedom of 7 line over to the alpha of 0.01, which is right here. 18.475 would be that critical value. All right, we're going to do one more together. So on the third example, we're looking for degree of freedom of 9 and an alpha of 0.10. So degree of freedom of 9 and alpha of 0.10, we're looking right here. 14.684 would be that critical value. Okay, guys, pause the video, try 4 and 5, and then unpause the video to get those answers. Okay, hopefully you paused the video. I found degree of freedom of 6 with an alpha of 0.05 as 12.592. I circled that one in orange. And degree of freedom of 10 with an alpha of 0.025. I got 20.483. That's circled in that light blue color. Okay, here is our test statistic formula for the chi-squared distribution. We have the chi-squared is equal to the sum of O minus E quantity squared over E, where O is the observed values, O equals observed value, and E is representing the expected value. Because we normally have more than one category, we would add those values up once we calculate for each category in the distribution. So you're going to repeat this O minus E quantity squared over E for every single category that you have, and then you would add up those values. Okay, we're going to practice finding just one chi-squared test component with this example. So it says, a supermarket expects to have approximately 70 customers in a day. On Monday, there were 63 customers that entered the store. What would the chi-squared test component be for this day? So on this particular example, guys, we're not going to have multiple categories that we're going to be finding the chi-squared summation of. We're just going to find this one. So it tells me that the supermarket expects to have 70 customers. So that's the expected value. That's E. But they actually had 63 customers. That's the observed value. So that's O. So in that last slide, it said that chi-squared was equal to the sum of O minus E quantity squared over E. We only have one category for this example. So we're just going to be doing this once. So we're not actually going to be utilizing the summation, the sum of symbol. We're just going to be doing this portion of the formula. Okay, so my observed value is 63 minus the expected value was 70. We square that difference and divide by the expected value, which again was 70. If I do that math, 63 minus 70, that gives me negative 7 squared over 70. Negative 7 squared is 49, again, over 70. And if I divide 49 divided by 70, I would get 0.7. So my chi-squared test statistic component for just this one category is 0.7. Okay, you guys try this one. Pause the video, see if you can find the test statistic component for this scenario. It's very similar to the last one. I just changed the day and the observed number of customers, and then unpause the video to get the answer. Okay, hopefully you've had time to work that out. The observed value in this scenario was 87, and the expected value was again 70. So we take 87 minus 70 squared and divide it by 70. I got a difference of 17. Squaring that gives me 289. Dividing that by 70, and I get 4.13. So if we compare those last two examples, we see, guys, that if the difference is small, we get small chi-squared test statistic components. For larger deviations, larger variances from what we expect, that's when we get larger values for the chi-squared test statistic component. It actually does not matter if it's below or above what's expected because we are squaring those differences. So it doesn't matter if I have a negative inside here or a positive. When I square those values, it is always going to be a positive result. So that's why we never get negative values for a chi-squared distribution. Okay, guys, we've kind of introduced ourselves to certain topics with chapter 11 today. On Monday, we are going to be talking about what's called the goodness of fit test for chi-squared distributions.